Well, I'd like to welcome you to Celebration of Faculty Careers. Of course, all my colleagues in the room know me. Today I'm actually serving as Associate Dean of the College of Engineering, so on behalf of the college, I'd like to welcome you to this celebration. The goals of this is to, one, recognize the work that Antonio has been doing over the years and celebrate his accomplishments. And so he's been here actually for quite a few years now.
17.
So I think we started almost the same time in
Right,
1997.
right.
And then in 2008 he was promoted to full professor. So actually we've been here about the same, I said on the same track.
Right.
But the other thing is that we're looking towards the future too. And so while it's a celebration of what's been accomplished already, Antonio has many years to continue working with us here in the college and a lot of accomplishments that will come in the future. So part of it is kind of looking forward to the future and what some of the work that you've done and how it's going to lead off to the future. So,
Absolutely.
Antonio, I don't want to take the time away from you, but thank you for presenting
My
today,
pleasure.
and we're glad to have you as part of the college.
Thank you. Thank you, Robert. Well, it's a pleasure to be here. Let me, since I'm going to show you some pictures, let me dim the lights a little bit. I hope we check it before. Should be okay. All right. Okay, so as I said, thank you for inviting me here. And as I was thinking about the presentation, I thought it would be also a good opportunity to look at least my thoughts about where there are opportunities, and of course every opportunity is a challenge, in geoengineering. I'm looking at this word as a very encompassing word. This is not soil mechanics, this is not rock mechanics. I want to go beyond geomechanics to geoengineering. And I put here this picture. This is one of my students that Mutlu graduated in 2005 that made the front page of the newsletter of engineering that says our programs speak for themselves. And I think that that's a good idea as we move forward, that at the end our programs are going to be speaking for themselves. So this is the outline of my presentation. What I have is like three broad topics, if you will. Now, the first one is what are the challenges that I see in geoengineering, and describe like three projects where I've been fortunate to participate with many of you, and how I see that these projects have contributed to move along this direction of the challenges and the things that I think we could do. Briefly, a little bit to show a little bit the impact, how this work has been recognized, and then finalize the presentation with this idea, where I think we should be going to continue with the impact and even increase the impact. So what are the challenges that I see in this field on geoengineering? And these are my thoughts. That doesn't mean that there are others. Other people may think that they may not be that critical. But if I'm looking at the needs that we have as society this century or even centuries to come, I think that there is a challenge of our aging infrastructure in the worst world. We have an infrastructure that is old, is at capacity, is not very well maintained. The cost is going to be tremendous. The scale is unimaginable. And the issue is what are we going to do with this? Are we going to renew it? Do we have the technology? Do we have the tools to do that efficiently in an economic way? Then we are looking also for new sources of energy. We're having these talks every day about unconventional resources, natural gas, thermal energy. This energy also has to be sustainable. And what are we going to do with all the waste that we are generating, for example, nuclear waste or CO2? Okay, so these are challenges that are facing us right now and is going to facing the next generations. And finally, we are pushing the envelope. We are building deeper, larger, bigger in environments that before we did not, we were not involved with. And the science to do those is not there yet. We are trying to extrapolate from what we know to environments that we are not that familiar. And we have to do that because that's the way we are moving forward and making progress. So these are the challenges that I see we need to deal with those. And these are the problems or the description or the ingredients to face these challenges. These challenges are multi-physics and multidisciplinary, while there is opportunities to make progress in each other's disciplines. And that's fine, and it's necessary. I think there are bigger, even larger opportunities to look at the interface among disciplines, because there's a lot to learn and do together. The second thing is that I think there's an opportunity to change the way we think. Traditionally, in my field in geoengineering, the approach to design has been, this is the ground. How are we going to design such that our design adapts to the ground conditions that we have? Okay? We are reaching the point that I think that it's good to think outside the box and maybe think with a different paradigm. And it's how we can change and adapt what we have to the needs of our project. Okay? And finally, I think that the other tool that we need to develop is make the Earth transparent. To be able to see, on a very broad sense, what we are doing, what are the impacts, how far, how deep, how is this going to impact other things, the environment, for example, how our fracking is going to have an impact on an aquifer, or how it's going to induce an earthquake. We need to be able to develop these tools. So what I want to do is show you 3 projects that I feel that have been successful, and some of you, as I said, are familiar because we worked together on these projects, where I think that they illustrate some of these ideas, some of these thoughts that I put forward. One is a project that is in collaboration between structures in geotech, that we were looking at a very interesting failure, the failure of the Daikai station in Japan. The other one is a project that illustrates this change in paradigm, okay? How we modify the ground, the soils, our materials, such that they adapt to our needs. And for example, here I show you a picture of, this is a sand, okay? This is a wet sand. And since we are all engineers here, I guess that all at some point we had the curiosity to go to the beach, excavate on the beach, right? And at some point there is a depth when you cannot excavate anymore because you find the water table and that the thing collapses and that's it, right? So this is a wet sand and it's supporting 50 or 60 years of knowledge in soil mechanics. So how we have done this, right? So that's a change in paradigm. And the other one is transparent earth, so how we can develop tools that are going to allow us to see inside of our materials and monitor the changes that we induce in these materials. So let me start with these 3 projects. I'm just going to provide a description. I don't want to go in depth, but I want to send forward the message about the possibilities that we can achieve working together. Okay? So this is the first project, that is the failure of the Daikai station in Japan. This is a picture of the inside of the station after it collapsed, after the 1995 earthquake. These are central columns, and you see the type of failure that occurred. We'll go with that in a minute. But you see, these are the people that collaborated in this project. Dr. Huo is the student who worked on that. Dr. Fernandez from the University of Illinois, from Geotech. Dr. Ramirez, who is here, was the lead on the project, actually, from Purdue. Dr. Sozen, Dr. Para Montesinos, at that time at the University of Michigan, also in structures, now at Wisconsin, and Dr. Maekawa at the University of Tokyo, and that was funded by NSF and also from Purdue. So that's a little bit of an overview of the consequences, if you will, of the Kobe earthquake in Japan in 1995. It happened in January. It was a magnitude 6.9, not a significant magnitude, except that the epicenter was very close to the city. This is the city of Kobe. This is the bay of Osaka. Locally, there were accelerations of about 0.8 G, but to see a little bit of the magnitude of the destruction, there was like 5,000 people who were killed, about 300,000 people homeless, about 50,000 people injured, about $150 billion of damage. And that's because there are soft soils here that amplify the earthquake. And then what happens in these earthquakes is that what we call lifelines, these are the pipes that transport energy and water, for example, gas, they break. And they break, and then they produce fires. And the fires cannot be extinguished because the water that could be used to extinguish the fires, also these mains broke. So there is a lot of damage that is produced in addition to the earthquake. However, for this particular case, I'm going to concentrate on this tiny little station here, which is the Daikai station, that collapsed during the earthquake. This is the view of the road on top of the station. This is Road 28. And you see this settlement, this sagging of about 2.5 meters above the road because the station underground collapsed. Okay, so this is the cross-section of the station. This is the station before the earthquake. This is the station after the earthquake. It's about, has an overburden about 4 or 5 meters. It's a reinforced concrete, 17 meters wide, about 7 meters tall. It was constructed by the method of cut and cover. So that means that we excavate from the surface, we build the station, and then we cover it up, so on and so forth. And you see this little column here, and that's the culprit of the failure, because this column failed. It couldn't absorb the deformations imposed by the earthquake. It failed in shear. That was part of the results that we did. Then the top slab lost the support. It collapsed, and with that, the collapse of the station. Now, why is this relevant? Well, it's relevant in many different ways. One, because, hey, this is a large-scale laboratory that we have with lots of data, and it's a great opportunity to look into that and see what happens. But even more interesting is that there is this perception, and I think this is one of the things that we need to do, is challenge every time what we are told that is being done, because it's always done like that. So underground structures, there is the perception out there that they are safe during earthquakes, that you don't have to design them to resist dynamic loading. Now, that was the first station that collapsed that was well documented. And then let me qualify that in a minute.
Is there a simple reason why that was believed? Why underground stations are not as successful?
Exactly. There is no reason. People think that they are safe. So that message is passed along, and it's safe, and then we don't design for seismic loading on the ground stations. That was not designed, and it collapsed. Okay. So then the questions, if you will, moving forward, is this an exception? Is this the norm? And then, even if people are doing some design, is it correct or not? Because, things are taken for granted, and maybe nobody has given much thought about that. Have I answered your question? So we keep doing things because that's the way we've been doing forever, and sometimes it's not right, and we need to question those. Okay, so these are some pictures of the station after the collapse. So these columns, and you see these longitudinal bars that buckled, and the reason that they buckled is that they didn't have enough transverse reinforcement. And, after seeing these pictures, it was clear right away that the reason for the collapse of the station, there was not enough transverse reinforcement. But the fundamental question was, what are the load and displacement transfer mechanisms that occur in the soil, between the soil and the structure? And that was a problem that was not a geotech problem, and it was not a structures problem. It was a geotech and structures problem. Okay, we needed to put the two things together to understand the problem and move forward and provide recommendations, analyze the problem, and see, is this an exception or is this the norm? So this is a plan view of the station. All that part of the station collapsed. This is about 110 meters, 30 of these columns collapsed. This is the access to the station that suffers some damage but did not collapse, and these are the tunnels between the stations. A little bit of damage, no collapse. So basically, we need to look at this, and there are questions. Why this collapsed? Why this didn't? Why this didn't collapse? And how, the soil is interacting with each of these sections of the structure such that the response is going to be different. So this is the cross-section of the structure that collapsed. This is the tunnels. This is the access station, just to have an idea that the cross-sections are different. But then, why they behave differently. This is the earthquake that we use for our model. It was I would say a fairly sophisticated model, fully dynamic, non-linear from the soil, non-linear from the structure, about 0.58 G horizontal, 0.16 G vertical at a depth where there was a steep layer. And then what we did was look at the response of the column, and you see that this column had a peak displacement of 4 centimeters. Of course, this was theoretical. The column failed here. But we wanted to see what would have happened. Then we used these displacements to input that into a sophisticated structures and concrete and steel reinforcement model to see if, with this input that we got from the soil structure interaction, that was enough to produce the collapse of the structure. And most importantly, if we did the same analysis on the other sections, was were the displacements small enough or not enough to produce the collapse, and if not, why not? So we discovered very quickly that that was not a load-driven problem. It was a displacement-driven problem. These are the displacements that need to be compatible between the soil and the structure. And a consequence of that was that what is important is the relative stiffness of the structure with respect to the soil. So the reason why this structure collapsed and these did not, apart from the geometry, was that their stiffness was different than this one. So that provides us a clue to move forward, and as we have to make recommendations, what sort of recommendations are going to make to practitioners, if necessary, such that these structures could be properly designed. Then the question is this an exception, or is there a pattern of mishandling and not realizing what happens in underground stations? So we began to look at what is happening out there, what has been reported. So this is a sketch of the rapid transit system in Kobe, and you begin to see that there is a significant report of damage. Here in this station, 5 columns, they were damaged, 200 in the tunnels. This one collapsed, an underground shopping mall with damage, mountain tunnels of the Shinkansen, they had damage. Then we dug a little, even a little more, and there was just barely, very little work done statistically on damage on tunnels. But then the evidence was compelling. So we look at these 70 cases that were compiled on tunnels. It's just not much. Here, what is the case number as it comes from the literature? But you begin to see that there are thresholds that people put saying, well, there is no damage for low accelerations. They collapse at accelerations that are above a threshold. The threshold is not that important because we learn more about that. But if you look at the number of cases that had damage compared to the total number of cases analyzed, 50% of the cases had damage. Then other people compile even larger databases. And they classify that depending on the depth. And sure enough, the shallow tunnels can be more damaged or have more damage than deep tunnels, depending on the type of soil. But look at this. About 50% also of this extended database, there is damage. Recently, 2001, the Chichi earthquake. Look at the statistics, number of cases, and the type of damage because a tunnel crosses a fault. Of course, there is no chance for the tunnel. It collapsed, right? But you look at the portals or you look at the damage inside of the tunnel, and 80%, 90% of the cases that people have looked at had damage. So it's not an exception. When there is an earthquake, tunnels get damaged, and tunnels need to be designed for seismic loading. Some pictures about what type of loading. This is one of the mountain tunnels. So behind this, there is this bedrock. It's not a soft soil. It's just rock. And you see at the invert, there is a significant damage, collapse of the spring line with buckling of the steel reinforcement. This is the Longxi tunnel after the Wenchang earthquake. Damage at the portals, damage inside, and a section that collapsed. So, it's a structure that is sensitive. Maybe it's not as sensitive as above ground structures, but it's sensitive to seismicity. And then we look at, how people dealt with the design of tunnels. And, there is a school of thought that says, hey, don't do anything because it's not needed. Well, I think we have discussed that already. Then there is a school of thought that said, well, what we do, and that's what they did for the restoration of the Daikai station, what you're going to do is impose to the tunnel, to the structure, the deformations that the soil has as there was no tunnel, okay? And you say, well, let's think about that in a minute, because what we're doing is the following. Let's do a thought experiment. And thought experiments are very cool because we can do whatever we want. Okay? They have to be run well. But let's do this thought experiment and see what this means. Okay? So this is a thought experiment. Let's suppose that I have the ground and I'm going to do something that is simple. Let's suppose that everything is elastic. It's not, but it's going to give us either it's right or wrong. So here it is. This is the soil, and I put a tunnel that has the same stiffness as the soil it replaces. Let's deform it with the earthquake. Sure enough, the tunnel is going to deform as the soil because basically we have not changed anything. Now, With these thought experiments, we are going to put a tunnel that is infinitely stiff. Okay? It's a thought experiment. The infinite, it's possible. All right. So we apply this deformation. The tunnel does not deform. So basically now we have a method that is going to provide a solution that is too conservative. Maybe we can live with it. But now let's suppose that they put a hole. Okay? It's a thought experiment. I can put a hole without support. But that means that the flexibility of this tunnel is going to be much larger than the soil it replaces. What happens? Now the tunnel deforms more than the free field by a factor of about 2 to 3. There is no factor of safety that is going to absorb this mistake. So, two big conclusions, or several conclusions. One is that structures, underground structures, are sensitive to earthquakes. They must be designed for earthquakes. Second, that is a prevalent problem. Third is that we are not designing well underground structures. And since then, we've done quite a bit of work going out and trying to educate people to say, hey, we need to design these structures. For example, one of the projects that I'm working on is with the design of the subway tunnel in Bogota. And they are concerned about the seismic design of the tunnel, and we are using what we learned from this project for the design of the tunnel in Bogota. And most importantly, I think we need to question all these preconceptions that we take for granted because they are passed from one person to the other along a chain and nobody ever questions those. Okay. Another project that I want to share with you where we've been working on this project for, I don't know, maybe 10 years, maybe 12 years. And this is the project where I think this change of paradigm from how we adapt the structure to what we have to how we adapt what we have to what we need. So this is a thought that came about after a workshop that we had here on adaptive methods that Professor Frosch organized. So the idea was, okay, that's an intriguing thought. Let's suppose that you could have a material, in this case a soil, that during normal working conditions does what is expected. Okay? But when there is an extreme event, like an earthquake, there is something in the soil that adapts to the new demands and survives that. Okay? All right. So that's what we did. We look at how we could get into the soil to change the soil without modifying its current conditions. So we thought of that rather than changing how these particles of the soil are arranged together, which is what we do, what we're going to do is get into the soil through the water, through the porefluid, okay? Because these are the conduits that are going to let us go inside of the soil. So that's what we call porefluid engineering. There's a number of collaborators here that have worked with that. The support has been steady from NSF for all these years. I think we have like 3 projects. We started with Haldavnekar in the late 90s. And we have one student who graduated recently, Chad Yalmotar. 2000. Okay. I was thinking before that. Okay. All right. Thank you. So Chad is now an assistant professor at the University of Austin, has received last year or so a career award to continue to work on a topic similar to that. There is many of us here that are listening to that, so don't say anything. If I say something wrong, come and see me later and tell me, but let me go. All right. So Alain is here, and Vince, we talk later, okay? So I don't know if Felipe is here, Professor Santagata is here, Professor Sinfield, and 2 colleagues, particularly Professor Johnson from agronomy, who was instrumental to help us with clay chemistry. And I'll mention that in a minute why that was critical. And also Professor Wei from chemistry. So you see also this concept of interdisciplinary looking at the specialties, at the interface, and but also in addition this change of paradigm. So we are looking at liquefaction, and what this phenomenon is. Those of you who are geotechs, you are very familiar with that. But this is a compelling picture that came from the failure of some apartment buildings in Niigata after the 1964 earthquake. The concept is very simple. We have a granular soil that is saturated. We shake it, and then what happens is that the pore pressure, the water, the fluid inside of the pores, increases its pressure. because it cannot get out of the pores. And it increases the pressure. What it does is tries to separate the grains from each other. And at the end, what we have is a thick fluid. And as a fluid, it has no strength. And it has no strength. That means that all the loads that are applied, they cannot be sustained. So there is this failure and these huge deformations. These are some pictures after the trip that we made, also with Professor Ramirez and others in Turkey. This is Adapazari, and you see the verticality of this building that was lost. Buildings destroyed, and this is downtown Adapazari. This is the middle of the street, okay? And this is where the buildings are. That's where the load is in the soil. And then you have a differential settlement of about 2 meters. And this differential settlement is produced because the soil under the building has lost its strength. Kind of a better of an engineering way, if you will. Here there's a number of plots. I'll go quickly through that. That's relatively important. But basically what you have here is axial strain. So these are samples, cylinders of soil that we put inside of a machine that we apply this cyclic loading. Nothing happens for a while, and then you begin to have huge deformations. And these huge deformations are associated with these pore pressures. This is the number of cycles to failure. And so you increase these cycles, and then this pore pressure that I was telling you increase until it reaches the confinement, the pressure that we apply to the soil, and then the soil fails. And this is a plot of the strength. We start here, and then we move backwards until basically we hit the failure envelope, and the strength of the soil is pretty much zero. A way of portraying, the strength of the soil against this liquefaction. The way that we do that is we present things that way. Here, basically, we put the demand on the soil. And here, we put the number of cycles that this demand can be resisted. And at the end, we can have on a log scale. We geotechs love log scales because everything linearizes very well. But anyhow, it's a way of looking at the data. So basically what you have is a line that gives you the strength of the soil for a given demand of the earthquake. Okay? So I'm going to go back to this plot because this is what we want to do. This is the soil that we have. Let's say that we have a clean sand. And what we want to do is move this line as much to the right as we can, because that means that for the same demand, the soil is going to resist a larger number of cycles. That means that it's going to survive the earthquake. An earthquake may have a duration of about 20 seconds, 30 seconds. So if we can have a soil that for a given demand can resist 100 or several hundred cycles, the soil will survive the earthquake. That means that the structures that we have will survive the earthquake. Now, why is this relevant? Well, because there are structures that we already have. Here is a picture of Evansville. This is where Evansville is, and it's very close to the Wabash Fault system. It's very close to the New Madrid. There's been significant earthquakes in the past. This is an alluvial area. Clean sands, loose sands, there's an earthquake. Chances are that there's going to be liquefaction here. Chances are that we may lose our bridges that connect Indiana with Kentucky, and we may have a significant problem. So, what are the solutions to upgrade or strengthen a soil? Well, one is the classical solution. We improve the soil, we go there, we mix it with cement, we densify, but that means that we induce significant deformations in the soil. Either the structures on top of it, the structures are not going to survive the strengthening. So the idea is maybe we need to change the way we think such that we keep the soil as it is without changing how it's going to deform through the treatment, but this treatment is going to be successful. So that's what we call engineering the soil. The idea came from this workshop, from this plot. This is a plot that has the demand on the soil and the resistance of the soil. And these lines here divide the survival of the soil. The soil here liquefies, the soil here liquefies, the soil here resists. And then the soil gets better as the percentage of fines inside of the soil gets larger. The more plastic the fines inside of the soil, the better the soil is in terms of liquefaction. So what is the clay that we know of that is the larger plasticity? Bentonite. And bentonite has characteristics of building this water between the layers, the double layers, so on and so forth. So the idea was, can we introduce bentonite into the soil? And would bentonite do what we want to do? So two big questions. If we have bentonite inside of the soil, will help with liquefaction. But also, when you have bentonite with water, you have a very thick paste. How how can we get this thing inside of the soil without displacing the grains, okay? So that's what we did with the idea that said, well, go to a site, these bridges in Ohio. We just put a deposit, we drill some borings, and then we let the thing permeate. And then we wait until whatever it is, and to do what this bentonite inside of the pores of the sand needs to be done. And then we have treated the soil without inducing deformations in the soil. So that's what we did. We started saying, well, is the concept right? So we ran some tests with sand and bentonite. This is the sand, this is the plot that I showed you before, number of cycles, strain, and sure enough, about 6-7 cycles, the thing goes. Now, if we introduce 3% bentonite, which is a fairly small percentage, we have 80 cycles. If we introduce 5%, we have 900 cycles, okay? So we go to this plot that I showed you before. That is the demand, that's the strength, that's the clean sand. What happens? This is 3% bentonite. We move this plot an order of magnitude, 5% bentonite. But wait, with time, this thing gets even better because we know that these slurries has some rheological properties, and their properties as a stiffness and viscosity increase with time. And sure enough, after 4 days, that's where we go. After 10 days, that's where we all have.
What happens?
What?
What happens?
Wait a minute. I'm getting there. So, not only that, this has healing properties. This is the confinement, that's how the thing degrades with pore pressure. The failure is here, 50 cycles, but that's the first test that we did in one of these tests. We let it sit for 24 hours, we cycle it again, and there it goes, 50 cycles again. So there is an inherent healing property of this material that is going to survive repeated earthquakes, or if there is damage, this damage is going to heal with time. So, why is that? What's going on? So this is the 10%, a kind of a fuzzy picture of the bentonite that seems like a jelly. This is bentonite with grains. So these are the grains that you see that are kind of covered with this sort of thick jelly. But then we went a little bit deeper, and these are scanning electron microscopes of the sand with the bentonite. And so now we begin to, I hope that we begin to see the picture. What we have is these sands, these sand grains, that are surrounded by this cellular structure, all the cellular structure, that's the bentonite, that provides a constraint to the movements of the sand grains. As the sand grains cannot move and they cannot collapse, we don't have this generation of excess pore pressures, and that's how these soils survive. So just a few pictures, pretty pictures about how this looks like. This is the cellular structure. This is the bentonite as seen from a scanning electron microscope, larger magnification. Much larger magnification, you see these walls that are made by large number of particles that provide this kind of isotropic. You see this structure is locally anisotropic, but on a larger scale is isotropic, and this structure provides, it's like a cellular type of structure that provides the stiffness to the sand grains that prevent liquefaction. But the big question remains, okay, so now we have this thing that we mix in the lab, but can we get it in, okay? So that's the clean sand. That's the clean sand with bentonite. We just get it in less than an inch. Well, if that's what we want to do, that would be the end of the story. But then the idea was, okay, so what can we do such that we can modify the chemical characteristics of the bentonite? And that's where we needed the help from people from chemistry and clay chemistry, such that initially we reduce the viscosity of this slurry, but once it's inside, because now we can permeate it, the process is reversible, and the thing gels inside of the sand, such that at the end, after a period of years, we are not in a hurry, because the earthquake is not going to happen in a month, hopefully, even though some people claim that can predict earthquakes. So that's the paradigm. So then that's the help that we needed. So we chemically treated the bentonite with sodium pyrophosphate, and as we increased the percentage of sodium pyrophosphate, we saw that we could permeate larger columns of sand. And here it is, that's the molecule of the sodium pyrophosphate. Why is that? Why is it happening? Because clay particles are electrically charged. And you have a negative charge here and a positive charge here, and they gel, and they get these rheological properties because they connect edges with the faces, and they create this kind of card structure. If we add a chemical that is going to satisfy the electrical charge at the edges, then we're going to have is a dispersed structure of the bentonite slurry, low viscosity, we can permeate it. This is a reversible process because there is a hydrolysis process that happens inside, and it's reversed. Here it is. This is a measure, it is a storage model, but it's a measure of how viscous this slurry is, and this is time. This is the untreated bentonite, the one we cannot permeate, and we cannot permeate it because these values are too high. As we increase the percentage of sodium pyrophosphate, now this property gets 3 orders of magnitude below, with time recovers to values similar to the bentonite. Okay? So that's the key of this business. Find a way to engineer what we need for the purposes that we need. And then how the soil with this permeated bentonite behaves, we see this significant increase, and this increase goes on with time. So I think there are opportunities to think a little bit outside the box, look at how we can engineer our materials such that they can adapt to our needs, but that can happen if we work together, particularly with other disciplines, where we can learn from each other about what we know, what we need. The final project that I want to share with you is an ongoing project, and it's about the imaging of sleep, and it's related to this concept of transparent Earth. What are the tools out there that we can develop or we can use such that we can see inside of the material, but kind of link these tools with mechanics, okay? Because we want to interpret mechanics with these tools, and we can use these tools to interpret mechanics. So this is a failure of a copper mine in Chile, and it's a failure associated with the idea that we are pushing the envelope of what we know. It's a very complex failure. So these are the collaborators. Choi and Hedayat have graduated. Now Amadreza is an assistant professor at IUPU Fort Wayne. 2 students working on that. And this is this project has been, we are thinking 4 years on this topic with Professor Piragnolti in physics. She has also a courtesy appointment with us. And that has been funded steadily also from the National Science Foundation. And this is basically the petroleum industry. So sleep, it seems that it's a concept. So again, we go back to this idea. We've been dealing with failure through sleep for ages. And we've developed all these models, and we think we understand the process very well. And yet, I don't think we do, okay? And just to illustrate how critical understanding sleep is, this is the Panama Canal. I'll tell you in a minute that I'm involved with that. This is the Gaylord Cut, where there was these huge landslides. And this is a picture of the inauguration of the canal in August 15, 1914. And some of you know that there is a huge project going on with building the 3rd set of locks. And a few months later, there was this big landslide closed the canal in October 1915. And this is one of the landslides in the area, and it's still moving. Okay, so there is some maintenance that needs to be done regularly to keep this thing checked. So in this project, we were questioning 2 concepts. One that seems trivial: how does sleep happen? And the second is how can we see from the outside what happens inside of this plane where sleep is occurring. Okay, so that's the partnering between mechanics, in that case me, and Laura Piragnolti from geophysics. So the experiments are straightforward. We have 2 blocks. These are rock material. It can be a model. It doesn't matter. Half of it, this part, we put a low friction strength interface. This one is rough, high friction. And then what we do with a contraption that we manufacture, we design and manufacture ourselves, okay? So we apply this confinement. This is a flat jack. These are some rollers to decrease friction. And then we apply the shear load with this other machine, and this is a spherical seed. We don't want moments, so on. Doesn't matter. So, but basically, what we have here in these caps is transducers. Transducers that are going to send P and S waves across the interface. And we're going to monitor those as we load this and as we fail the specimen. And at the same time, what we do, these are the transducers, so these are P or S transducers that we play with those. And what we do is at the same time, we use a camera to look at the front, and we are using digital image correlation to monitor how displacement occurs between these two blocks, monitor load and displacement, of course, and monitor how these P and S wave transducers, these waves behave as they cross the specimen, as the specimen is undergoing friction. And the question is what we learn from all those. So these are the P waveforms that you have along the smooth surface. So that's a kind of a front view of the specimen. That's smooth, that's rough. So that means that when you load it, we expected that this thing would fail first. Then there would be a buildup of stresses at the interface that would work as a crack. And then finally, at some point, you would have failure of the entire thing. So here, what you have is a P transducer across the smooth surface. Here, you have this S transducer also across the smooth surface. And of course, we have transducers everywhere. I'm showing you those just for information. And here, so this is the amplitude of the wave that we are sending as it is recorded on the other side. And that's time. OK, so now this part here, these numbers correspond to the displacement before or after peak load. OK, so 0 means that we are at peak. Minus means that we are not at peak yet. And positive means that we have passed the peak strength of the discontinuity. Okay? So if you look at those, we start with this -1 here, and the same here. I'm going to focus on that one. Then as you increase the load, meaning that you are getting closer to failure, what we see is these amplitude go up, right? It increases, as expected. We were expecting that. But then at about 0.25, then it peaks, and then it begins to decrease at peak, and then it further decreases. Okay? So two things. One is that this amplitude is very sensitive to what we are doing, so that's good news. But second is that, look at this. This is the P, this is the S. Something similar, the S's are clear, so I'm going to focus on the S. So these are the normalized amplitude. We start with 1, that's why it's called normalized. So this is a plot of normalized peak-to-peak amplitude. Shear displacement, that's where the 0 is at the peak, okay? And this plot here corresponds to shear stress displacement. That's the peak, 0 displacement. And you see at these normalized amplitudes, and what we see is that they peak way before peak. And then at peak, they begin to decrease. On the smooth surface, we practically lose contact. On the rough surface, we continue with the contact. And now we said, oh my gosh, we see precursors. We see precursors to failure. We have a tool that is giving us a kind of a signal that is telling us, hey, I reach a peak, I begin to decrease, I'm going to be failing pretty soon. But this is information that we have way before failure. So this is a movie, just a kind of, oops. Putting all this together, right? So this is the shear stress displacement. That's the peak and failure. And this is the normalized amplitude. These are two transducers, one on the smooth, one on the rough. And it goes as the shear goes. So you see they reach the peak. These are the precursors. And then they begin to go down, and at failure, they have a significant drop. But we can see failure before it happens. I mean, imagine the possibilities that this has. And also with the DIC, we were monitoring displacement as it happened. So you see, now this is the smooth surface, and now it fails. So it's going to loop again. So we start, nothing happens, and then you begin to see some slip here, right? There is a jump between the two sides. It's moving down, right? That's how it goes, and then it fails. We did a very limited number of experiments where we bond the two surfaces. We put a little bit of cohesion and see what happens. So nothing happens, pretty much nothing happens until cohesion goes. That's the point where there is the bonding between these two halves, okay? The bonding, At this point, there is the bonding. Not much happening here. Still the same process of the DIC. Reaches the peak and fails. We don't see much of a precursors. But we've learned two things with this test and other experiments that we did before. One is that we always think that failure happens through a combination of cohesion and friction. And it's true. The problem is that these two are not developed at the same time. First, with a small deformation, there is the bonding of the cohesion. Then we can keep with the strength. We don't understand still why we do that, but we keep with the strength and we mobilize the frictional strength of discontinuity. Second is that as we apply shear to discontinuity, the discontinuity suffers some damage. And this is the point here where there is a maximum damage because this amplitude reflects the stiffness of discontinuity and associated with damage. But after this peak has occurred, there is still some capacity of the discontinuity to take some load. We don't understand that. But what we do understand, what we do see, is these precursors. And as I said, we see this as a huge opening possibility to move forward. So a few conclusions. I went through that, so let me move forward. For the next 10 minutes, just to share you a little bit the impact that I think that some of this work has had. On my side, because of the work on underground structures, the PEC award in 2011, the award in Panama by Senatite in 2012, and I know that you don't see this gentleman here, but let me assure you that I was in good company. And that is the 2012 ARMA, American Rock Mechanics Association Research Award. In terms of service, a couple of years ago, I was the chair of the 46th U.S. Rock Mechanics Geomechanics Symposium that was organized in Chicago. I'm currently the president of ARMA since 2013. It's a 2-year term. It's going to expire in 2015. And I'm a member of the Geotechnical Advisory Board of the Panama Canal, and there is a number of students here who came with us, and Vince Drenovich also was there, where we went and visited the canal to look at the construction. We were very well received. Some people even danced, okay? Some people, okay. So, again, kind of wrapping up, go again where I started. These opportunities and vision. We've been through this slide. I think that there are huge challenges that our generation and the generations to come are facing that previous generations did not. One is this, the huge problem that we're having about aging infrastructure, the volume, the cost associated with that, the challenges, particularly because society is going to demand to keep this infrastructure going without disruption, okay? Second is that energy. We are always hungry for more energy because we are growing, but we need to keep the energy clean. We need to have a sustainable source of energy. We need to deal with our waste disposal. We are not doing it. It's a problem that is getting more and more pressing. Nuclear waste, CO2, and that we are pushing the envelope, starting to design and build in environments that we did not do it before. These are problems that call for a multi-physics, multidisciplinary approach. There are opportunities to change the way we think, and there are opportunities to develop new tools to monitor what we're doing. Go back to the Panama Canal, but now I'm going to focus here. So the canal was built by building these locks here, the cut here, and then cutting the Chagres River to create a lake that now the ships can go through, and then they go out through the Gatun Lakes. Now, because of the construction of the third set of locks, the Panama Canal Authority did a fantastic job, a seismologic job, looking at the sources of earthquakes that can occur in the area and try to quantify those. And guess what? This is the Gatun Dam. It was built in 1914 by the Army Corps of Engineers. It was built by a technique that is called hydraulic fill, which basically they were pumping. They created two berms here, rock berms, one here, one there, and then they would put some pipes and pipe soil with water to fill the space between the two berms. This is a technique that we've learned that is prone to liquefaction when there is an earthquake. Okay? So chances are that there is a moderate earthquake. We don't need a significant earthquake for the material inside of the dam to liquefy. That will create significant lateral deformations. It would crack the dam, open for internal erosion, and eventually the canal may lose the dam. If the dam is lost, the canal is lost. If the canal is lost, $60 billion per year income from the country of Panama is lost. Okay. So now the issue is what we do with this and how we strengthen that. So the solution that we are thinking is build a new dam. However, if there were technologies or techniques such as the one that I explained to you, where we can go inside of the pores, put these materials to strengthen, maybe we could come up with solutions that were not as invasive and probably not as expensive. Same thing here, right? These bridges that I told you that are on top of the Ohio River, that there is an earthquake, there may be problems with liquefaction, how we are going to upgrade those. So, we have techniques that we think in a different way such that we can upgrade those without disrupting the traffic. That would be something significant. Now, some of you have seen, that's the opportunities and the challenges as I see them. That's in new energy. That's the concept of hydraulic fracturing. We drill from the surface, horizontal drilling, and at some points we close these borings and we pump water at pressure and we create these cracks. And these cracks, what they do is they increase the permeability of the rock, and through this we capture the gas, the methane, or the oil. Now, problems associated with that is that these cracks that here are nicely drawn, that are just inside of this formation, they may connect this formation with others, and some of the chemicals that are used in here may contaminate the aquifer. As we change the state of stress inside of the ground, what we may produce is induced earthquakes. How we control this, how we measure that, the science is not there yet, and these are opportunities. Geothermal energy. This is a map of the US with areas where there is potential for tapping into geothermal energy. The process is very similar. We inject cold water, we fracture the area of the rock where there is significant heat because we want to increase the permeability, and we recover the water. Similar issues. We fracture, how we control that, how far they go, what is the environmental concerns associated with that. And this is compounded because we are dealing with an environment that has huge temperature, and we are not sure how to deal with those. And CO2, right? Now there is this idea of pumping CO2 inside of the underground. There are many different ways, and keep it trapped for thousands of years, and make sure that the cap rock is going to be intact, or at least the damage is going to be limited, such that the CO2 is going to remain here and is not going to find a path to get to the surface, because if it goes to the surface, the loss, particularly the life loss, is going to be huge. We cannot allow that. This is a project that I was involved in Switzerland. They were looking at sites for waste repository. This is the concept, again, some shafts to access to the level, some tunnels, and then these disposal tunnels where you're going to have these canisters with nuclear waste, high radioactive, low radioactive, that is going to be encapsulated there for hundreds of thousands of years. So how do we design a project that is going to be last with some credible factor of safety for thousands, tens of thousands, or even hundreds of thousands of years? We don't have the science and engineering to do that. This is a project I was involved with. This is the Lodgeberg Tunnel in Switzerland. This is a tunnel that is being built to cross the Alps. And this is a rock that has an unconfined compression strength of about 10 to 20 times more of the best concrete that we can produce. And yet, here it is, fractured as that was, something made of sugar. Why is that? because we are pushing the knowledge that we have and how we build these structures. This is a very large tunnel, it's about 9 to 10 meter diameter, but most importantly, it's at 2,000 meters deep. And at this level, there are pressures that are beyond what we've done in the past and beyond what we've been testing in our labs. So we need to deal with that. This is the same picture that I showed you before. This is 500 meters, okay? 500 meter excavation on a weathered rock, and now we begin to see failures that are not the typical failures that we are used to. Failures in rock, we always thought are going to happen through the discontinuities, not through the matrix, because the matrix was too strong for that. But it's a matter of how much pressure. And now we begin to see compound failures that involve pre-existing discontinuities and intact rock. Now this is a field that we have not explored. So, extreme environments. We are designing in areas and pushing things that are beyond our understanding. Anyhow, so these are my thoughts, a little bit the experience that I had with many of you, and I hope that you enjoy the talk. Thank you so much. You want questions?
Get the mic. I'd like to open up for questions. So
Yeah,
there's a
I have
mic.
a question
If you can talk in the mic, they are recording the.
Yes, very good, Antonio. My question is, you raised some of the issues that we're pushing with our known knowledge that we have, and that takes many things are not working out right. My question is, what we're doing in our geotechnical group that to extend that knowledge so we can do things right?
Oh, geotechnical group meaning here?
Yes.
Well, it's a little bit what I wanted to share with you. I mean, we are not doing everything that is needed, but we are doing something along these lines. One is that I show you these three examples where I think we are doing something along this direction. Example one, we identified a problem that was a problem, and we provide solutions for that problem, which is underground structures, right? The second thing is that there is a problem that we recognize in terms of infrastructure. You know, there is infrastructure that needs to be upgraded, and we cannot upgrade this structure if, A, the cost is going to be too much, or is going to have a huge impact on the user. Okay? So what we do to solve a problem, I mean, we are not solving the problem, but I think that what I would take from this, if I can so say, is that it's not only the particular example that I use, is a little bit the philosophy that one has to have approaching this. So the philosophy on the first problem was, I think we need to work together with other disciplines. Second thing is that I don't think we can take for granted what we've been told forever. We need to question things. The second thing on the second problem is that, hey, there may be solutions that are non-traditional. And I think that we need to think of those. We need to think of a non-traditional way to find solutions that are going to be as better or even better than the ones that we could accomplish being incremental. And the third one is that, hey, we need to not only look at the mechanics, but we need to find a way of trying to measure the effects of the mechanics with some system that is going to be non-destructive. And couple the two, because if we are able to develop a technology that we can look inside of our ground and say, I'm putting this foundation, I'm drilling this borehole, I'm doing this hydraulic fracturing, and we see how is this affecting this network of other fractures. Or we can predict if a fault is going to go, and we can provide, a time between failure of an earthquake that is going to be hours or days. I think that is so. We are doing things. We cannot do everything, but we are doing things, Kumar.
But doesn't the knowledge that we have in soil mechanics, like Terzaghi's theory of consolidation, they have not been proved wrong?
No.
So
what they've been proven is that they are good within the framework where they were developed. In the sense that if now you begin to put temperature, now you begin to put large rapid loading, then you need to come up and say, well, these theories, they were developed 50, 60 years ago, where we had these type of needs. Now we may need to expand those, and we have to be open to expand those.
Very nice overview, Antonio. Thanks a lot. I want to ask you a non-technical question. So,
Okay, like that.
if you were to name one thing, what would be the most important, the key to your success?
Other people. I mean, you look at these. None of these. So I haven't shown you any project where I work alone. I don't know. Maybe that says something. I think that there is. So working with other people is very difficult. Okay, it's very difficult because you not only have to have similar interest. So that means that has to be some time that you dedicate to see what others' interests are. There has to be some chemistry. That there are some people that you can work with, others that maybe it's going to be a little bit more difficult. So I think it's other people, Panagiota.
Yeah, sounds great. Thank you.
Well, if there's not any other questions for you, any other? Again, Antonio.
Beans is.
He's
no?
dying.
Okay.
He wants us to
All right. Okay. Thank you. I appreciate that.
Well, I'd like to thank you very much for presenting this afternoon.
Thank you for coming.